Alright, we want to take a look at Newton's third law. Essentially, I've got three masses here. If I want my three masses to move, and they're all in contact with each other, I only need to apply force to one of them, and then you're going to take a look, they all move in unison. So they would all have the same rate of acceleration, and so what we'll do, in order to kind of analyze how the third law works, is just take a look at a mass of 1, let's say a mass of 2, and a mass of 3. And what we're going to do is we're going to apply a force to only one of the objects. So we're only in contact with this object here. We're going to apply a 12 Newton force to that object. Now what we see is that they all move in unison, so they would all have the same rate of acceleration. So let's diagram out the horizontal forces here. One has a 12 Newton horizontal force acting on it to the right. I can see why that would move to the right. 2, however, I'm not touching it, yet it moves to the right. So it's not me that does the pushing here. It's object number 1 that does the pushing. And let's try and color coordinate things here. It's object 1 that pushes object 2. So I'm going to call this F1 on 2. Then we've got object number 3 here. And likewise, it's not me that pushes it. It's object 2 that's in contact with it. It's F2 on 3. Now I can see why things move to the right, but we got to be mindful of the third law. The third law states that if one object pushes one, the other object's going to push back on the other. So essentially, if 1 pushes 2, we expect 2 to push 1. So we're going to have an action-reaction pair here, where these two forces are equal in size, but clearly opposite in direction. And then for the same reason, if 2 pushes 3, 3 has to push 2 back the other way. Now looking at those forces there, what I have is basically bunch of unknowns. I don't know what this is, this, or this, but I do know that these two are equal, and I do know that those two are equal. And if we write some second law expressions for our masses here, let's do one for mass number 1. It's a massive 1, so instead of writing m, we're just going to write 1 times a. I've got a 12 Newton force to the right, and F2 on 1 to the left. Two unknowns here. I really can't do anything with that. Let's look at the second mass. That's a mass of 2. It should have the same acceleration, so I represent it with the same variable a. And we have F1 on 2 to the right, F3 on 2 to the left. Three unknowns here. Let's do the third mass. 3a, F2 on 3. Now, what we have here is essentially a lot of unknowns here. However, some of them are equal to each other. For example, this and this have to be equal. And this have to be equal as well. So we can actually do a little bit of substitution here. Before we try to do any substitution, let me rearrange this. I'm going to call this F2 on 1. And I'm going to figure out what it would be. So if I moved it over there, it would be positive. If I moved the a over there, I would get 12 minus a here. And so this is going to help me, because what I can do is I can do a little bit of substitution. I can take this stuff and put it into there since they're equal, and I can take this and put it into there since it's equal. So I can put in 12 minus a in for F1 on 2 and 3a in for F3 on 2 into this middle equation here. And let's see what ends up happening. So 2a, leave that alone. In for F1 on 2, we're going to put in 12 minus a. And in for F2 on 3, there's a minus sign, and then we have 3a. Let's move all that to the left. You get 6a on the left equals 12. I want my acceleration here. That's going to be 12 divided by 6. 2 meters per second squared is my acceleration. So now I know how fast each of them accelerate. But let's actually look at the forces, because they're going to make a lot more sense when we look at it. Because right now, if I look at the 12 Newton force acting on the 1 kilogram object, I would expect an acceleration a lot more than 2, unless something else is also pushing back on it. But now that we know A, we can actually figure out what those forces are. So let's put in 2 for A there. And what I would quickly get is F2 on 1 is equal to 12 minus 2. F2 on 1 is equal to 10 newtons. So just plugging our value back in A gives us the force value there, and that means that these two forces are both 10 newtons. Now this actually makes perfect sense, because I got a 12 Newton force to the right a 10 Newton force to the left, that's a net force of 2 acting on this mass. I can see why it would have an acceleration of 2 meters per second squared to the right. We can also figure out this pretty quickly because F2 on 3 is equal to 3A, so that would mean it's equal to 3 times 2. I guess this is a 6 Newton force. Now, the fact that this is just a 6 Newton force acting on a 3 kilogram object, I can see why this would have an acceleration of 2. But let's put it over here as well. I've got a 6 Newton force to the left here. So 10 to the right, 6 to the left, that's a net force of 4 acting on this mass here. It all makes sense from a forces perspective. So we had to do a lot of algebra to get the acceleration here. And, you know, it does work, but let me point out one other thing here. There was a shortcut to this problem in figuring it out. We do have the option of just considering all these 3 masses as one entity. We could have simply said, okay, those 3 masses look like this, and they're 1 plus 2 plus 3. They're a total mass of 6, and essentially, when we look at our external force of 12 newtons, I can see right away, well, if I have that force acting on that object there, I could solve for A pretty quickly and get 2 meters per second squared using sigma F equals ma. So that is a shortcut considering that this is an external force. Now, what I want you to realize here is that we are now ignoring all the internal forces that exist between the objects that we have grouped together. So when you group them together, you only consider external forces. The other thing I would like to point out here is that every single force up here has an action-reaction pair, except this one. And it's not as if this one acts in isolation. There's got to be somebody that's doing the pushing, and they're applying the 12 Newton force. So this object has to actually push back on them with a 12 Newton force as well. So once we account for that, now we've identified everything that has an action-reaction pair.